What if everything we think we know about the universe is just the tip of the iceberg? Hidden in the depths of space are phenomena so bizarre, so incomprehensible, that they defy the very laws of physics as we understand them. These are cosmic singularities, points where gravity becomes infinite, time distorts, and reality itself seems to unravel. From the crushing depths of black holes to the explosive birth of the universe in the Big Bang, singularities challenge our deepest assumptions about existence. But here's the thing, understanding them could rewrite the rules of science as we know it. In this video, we're diving into 20 groundbreaking theories about cosmic singularities, ideas so radical, they might just change the way you see the cosmos forever. Are you ready to explore the universe's greatest mysteries? Let's begin. At the heart of every black hole lies a mystery so profound, it threatens to unravel the very fabric of physics as we know it. These cosmic giants, born from the collapse of massive stars, are defined by their singularities, points where gravity becomes infinitely strong, and the rules of space-time cease to apply. Picture this, a realm where matter is crushed into an infinitely dense point, where volume shrinks to zero, and where our equations simply break down. It's a place where the familiar laws of the universe seem to surrender, leaving us with more questions than answers. But here's where things get even stranger. According to classical physics, the singularity at the center of a black hole is a point of no return, a place where time and space collapse into an unknowable abyss. Yet, quantum mechanics hints at a different story. Some physicists argue that at such extreme scales, quantum effects could prevent the formation of a true singularity, instead creating a kind of quantum foam where spacetime fluctuates wildly. Others go even further, proposing that black holes might not be the end of the road at all. Could they be portals to other universes, or perhaps cosmic recycling centers where matter is reborn in new forms? This paradox forces us to confront the limits of our knowledge. If singularities truly exist, they challenge the very foundations of physics, pushing us to rethink what we believe about space, time, and the nature of existence itself. Are black holes the ultimate cosmic dead ends, or are they gateways to something far more extraordinary? The answer, for now, lies hidden in the shadows of these enigmatic giants, waiting for science to catch up to the mysteries they hold. The Big Bang is often hailed as the dramatic beginning of everything, the moment when time, space, and matter burst into existence. But what if this singular event was just one spark in an endless cosmic fireworks show? At the heart of the Big Bang lies a singularity, a point where density and temperature reach infinite values, and our current understanding of physics simply can't keep up. It's a concept that's as baffling as it is fascinating, raising questions that go to the very core of existence. Why did it happen, and more intriguingly, could it happen again? Some scientists propose that the Big Bang wasn't a one-time event but part of a grand cosmic cycle. Imagine a universe that expands, contracts, and then explodes anew in an endless loop, a process known as the Big Bounce. In this scenario, the singularity at the start of our universe might not be the beginning of everything but rather a turning point in an infinite sequence. It's a theory that challenges the idea of a linear timeline, suggesting that the universe could be far older and more resilient than we ever imagined. But what if our universe isn't alone? Enter the multiverse theory, one of the most mind-bending ideas in modern cosmology. According to this concept, the Big Bang singularity might not be unique to our universe. Instead, it could be one of countless singularities, each giving rise to its own separate reality. Picture an infinite cosmic tapestry, woven together by countless threads, each representing a universe with its own laws of physics, its own stars, and its own potential for life. It's a humbling thought, one that forces us to reconsider our place in the grand scheme of things. the idea of a multiverse doesn't just expand our understanding of the cosmos, it challenges the very notion of uniqueness. If there are infinite universes, each born from its own singularity, then our universe is no longer the center of existence but just one among many. This raises profound questions. Are we alone in the multiverse, or do other versions of us exist in parallel realities? And if so, what does that mean for the concept of destiny? As we grapple with these questions, one thing becomes clear. The Big Bang Singularity is more than just a scientific puzzle. It's a gateway to understanding the nature of reality itself. Whether it's part of a cyclical process or a single thread in a multiverse tapestry, the singularity at the beginning of time continues to push the boundaries of human knowledge. And as we explore these theories, we're not just uncovering the secrets of the cosmos, we're redefining what it means to exist within it. What if singularities aren't just cosmic vacuum cleaners, sucking everything in, but also cosmic fountains, pouring energy and matter back into the universe? Enter white holes, the theoretical opposites of black holes. While black holes are infamous for their inescapable gravitational pull, white holes are thought to be regions where nothing can enter, only escape. Imagine a singularity running in reverse, where matter and energy burst outward instead of collapsing inward. It sounds like science fiction, but white holes emerge as legitimate solutions to Einstein's equations of general relativity, the same framework that predicted black holes in the first place. So why haven't we found a white hole yet? The truth is they're purely theoretical, and their existence remains unconfirmed. But if they do exist, they could explain some of the most energetic and mysterious events in the cosmos. Take gamma-ray bursts, for example, sudden, intense flashes of energy that light up the sky for mere seconds before vanishing. Could these be the signatures of white holes, releasing pent-up energy in a cosmic outburst? It's a tantalizing idea, one that challenges our understanding of singularities as purely destructive forces, but here's where it gets even more intriguing. Some scientists speculate that white holes could be connected to black holes through a cosmic tunnel known as a wormhole, a shortcut through space-time that links two distant regions of the universe. In this scenario, what falls into a black hole might not be lost forever, but instead expelled through a white hole elsewhere. It's a concept that blurs the line between destruction and creation, suggesting that singularities might not be dead ends but rather cosmic highways, transporting matter and energy across vast distances. Of course, the idea of white holes raises as many questions as it answers. If they exist, why are they so elusive? Are they inherently unstable, collapsing almost instantly after forming? Or could they be hidden in plain sight, masquerading as other cosmic phenomena? These questions push the boundaries of astrophysics, forcing us to rethink the nature of singularities and their role in the universe. What's truly remarkable about white holes is how they challenge the notion that singularities are one-way streets. Instead of being in points, they might be part of a larger cosmic cycle, a dance of matter and energy that we're only beginning to understand. Whether or not white holes are real, their very possibility opens up a universe of new questions and possibilities, reminding us that the cosmos is far stranger and more dynamic than we ever imagined. Now, let's venture into a realm where the rules of the universe seem to unravel completely. The enigmatic concept of naked singularities. Unlike black holes, which cloak their singularities behind an event horizon, naked singularities are thought to exist without this cosmic veil, exposing their infinitely dense cores to the outside universe. Imagine standing in front of a phenomenon so extreme that it defies the very laws of physics, where gravity spirals out of control and space-time itself becomes a chaotic mess. It's a scenario that challenges one of the most fundamental principles in astrophysics, the cosmic censorship conjecture, proposed by physicist Roger Penrose. the cosmic censorship conjecture suggests that singularities must always be hidden behind event horizons, shielding the universe from their unpredictable and destructive effects. In other words, nature abhors a naked singularity. But what if this isn't always the case? If naked singularities exist, they would shatter this cosmic rule, creating regions where the laws of physics as we know them no longer apply. The implications are staggering. Without the protective barrier of an event horizon, the intense gravitational forces of a naked singularity could wreak havoc on spacetime, making it impossible to predict how matter and energy would behave in its presence. This breakdown of predictability raises profound questions about the nature of the universe itself. Physics relies on the idea that, given enough information, we can predict the future state of a system. But a naked singularity would introduce an element of chaos so extreme that even our most advanced equations would fail. It's like trying to forecast the weather in a storm that rewrites the rules of wind and rain as it rages. Could such a phenomenon exist, and if so, what would it mean for our understanding of causality and the orderly progression of time? Some researchers argue that naked singularities might form under specific conditions, such as during the collapse of certain types of stars or in the chaotic aftermath of cosmic collisions. Others suggest they could be relics of the early universe, left over from a time when the fabric of spacetime was still settling into its current form. While no direct evidence of naked singularities has been found, their theoretical existence continues to spark debate and curiosity among scientists. What makes this theory so captivating is not just its challenge to physics, but also its philosophical implications. If the universe can produce naked singularities, it suggests that there are regions where predictability fails, where the future becomes inherently unknowable. This idea forces us to confront the limits of human knowledge and the possibility that some aspects of the cosmos may forever remain beyond our grasp. Naked singularities remind us that the universe is far stranger and more unpredictable than we often assume. Whether they exist or not, the very idea of them pushes us to rethink the boundaries of science and the nature of reality itself. And as we continue to explore these cosmic mysteries, we're not just seeking answers, we're learning to ask better questions. What if the key to unraveling the mystery of singularities lies not in the vastness of space, but in the tiniest fabric of reality? Enter the world of quantum singularities, where the rules of the universe take a dramatic twist. Unlike the predictable, albeit extreme, conditions of classical singularities, quantum mechanics introduces a layer of uncertainty that could fundamentally alter how we understand these cosmic anomalies. At the quantum level, nothing is certain, everything is governed by probabilities, and the very fabric of spacetime becomes a fuzzy, fluctuating entity. This raises a fascinating question. Could quantum effects save us from the infinities that plague classical singularities? Or do they open the door to entirely new kinds of singularities we've yet to imagine? To grasp this, let's start with the concept of uncertainty, a cornerstone of quantum mechanics. In the quantum realm, particles don't have definite positions or momenta until they're observed. Instead, they exist in a cloud of probabilities, constantly shifting between states. When applied to singularities, this uncertainty could mean that the infinitely dense points predicted by classical physics might not actually form. Instead, quantum effects could smooth out these infinities, creating a kind of quantum fuzz where spacetime remains finite, albeit highly distorted. It's like trying to pin down the exact location of a shadow. It's always just out of reach. This idea isn't just theoretical, it's supported by some of the most cutting-edge physics. For instance, string theory, one of the leading frameworks attempting to unify quantum mechanics and general relativity, suggests that singularities might be replaced by fuzzballs complex, quantum entities where the traditional notion of a singularity dissolves into a tangled web of strings and energy. It's a radical departure from the classical view, hinting that the universe might be far more intricate and less chaotic than we once thought. But quantum singularities don't just solve problems, they create new ones. If quantum effects prevent the formation of classical singularities, what replaces them? Could there be quantum singularities that behave in entirely unexpected ways, governed by the strange rules of quantum mechanics? Some physicists speculate that these quantum singularities might act as cosmic bridges, connecting distant regions of space-time in ways that classical singularities never could. Others suggest they might be the seeds of new universes, birthing entirely new realities from the quantum foam. The implications of this theory are profound. It not only challenges our understanding of singularities, but also forces us to rethink the relationship between the microscopic and the cosmic. Quantum mechanics, once thought to govern only the smallest particles, might hold the key to understanding the largest structures in the universe. It's a reminder that the cosmos is far more interconnected than we often realize, with the tiniest quantum fluctuations potentially shaping the fate of entire galaxies. As we explore the possibilities of quantum singularities, we're not just probing the limits of physics, we're also confronting the limits of our imagination. Could these quantum anomalies be the missing link in our quest to understand the universe? Or are they just another layer of mystery waiting to be unraveled? One thing is certain, the journey to uncover the truth about singularities is far from over, and quantum mechanics might just be the compass guiding us through the unknown. What if the information swallowed by a black hole isn't lost forever, but instead stored in a way we've never imagined? This is where the holographic principle comes into play. A mind-bending idea that reshapes how we think about singularities and the very nature of reality. At its core, the holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram stores a three-dimensional image on a two-dimensional surface. When applied to black holes, this theory offers a radical new perspective. The information devoured by a singularity might not vanish into oblivion, but instead be imprinted on the black hole's event horizon, the point of no return. This idea challenges one of the most perplexing puzzles in physics, the information paradox. According to quantum mechanics, information about the state of a system can never be destroyed. Yet, black holes seem to defy this rule, sucking in matter and energy along with all the information they carry, seemingly erasing it from the universe. The holographic principle offers a potential solution. Rather than being obliterated, the information could be encoded on the event horizon in a way that preserves it, even as it becomes scrambled and unrecognizable. It's as if the black hole acts not as a cosmic shredder, but as a cosmic hard drive, storing data in a form we're only beginning to understand. But how does this work in practice? Imagine the event horizon as a vast, intricate tapestry, with every particle and wave that falls into the black hole leaving a unique mark on its surface. These marks or bits of information might be incredibly complex, but they're not lost. Over time, they could even be decoded in theory, allowing us to reconstruct what fell into the black hole. It's a concept that bridges the gap between quantum mechanics and general relativity, two frameworks that have long struggled to coexist. What makes the holographic principle so compelling is its ability to reconcile the seemingly irreconcilable. It suggests that singularities, regions of infinite density and gravity, might not be the chaotic, destructive forces we once thought. Instead, they could be part of a deeper, more ordered structure where information is preserved in ways we're only beginning to grasp. This idea has profound implications not just for black holes, but for our understanding of the universe as a whole. If the holographic principle holds true, it could mean that the cosmos operates like a vast, interconnected hologram, with every piece of information encoded on its boundaries. Of course, this theory raises as many questions as it answers. How exactly is information encoded on the event horizon? Could it ever be retrieved, or is it forever locked away in a form we can't access? And what does this mean for the ultimate fate of matter and energy that falls into a black hole? These questions push the boundaries of our knowledge, challenging us to rethink not just singularities, but the very fabric of reality. The holographic principle reminds us that the universe is far more mysterious and interconnected than we often assume. It hints at a deeper order underlying the chaos, a hidden structure that governs the behavior of even the most extreme cosmic phenomena. As we continue to explore this idea, we're not just unraveling the secrets of black holes, we're uncovering clues about the fundamental nature of existence itself. And in doing so, we're stepping closer to understanding the true complexity of the cosmos. If black holes are the universe's one-way streets, could wormholes be its cosmic highways? These theoretical tunnels through space-time have long captured the imagination of scientists and science fiction fans alike. At their core, wormholes are thought to contain singularities, points where the fabric of space-time bends so drastically that it creates a shortcut between two distant regions. But unlike the crushing, inescapable singularities of black holes, wormholes might offer a way to traverse the cosmos without being torn apart by gravity. The catch: they'd require something extraordinary to exist, exotic matter with negative energy. Here's how it works. According to Einstein's theory of general relativity, wormholes are mathematically possible, but they're incredibly unstable. Left to their own devices, they'd collapse almost instantly, snapping shut like a rubber band stretched too far. To keep a wormhole open, you'd need a substance with negative energy, a kind of exotic matter that defies the usual rules of physics. This bizarre material would counteract the immense gravitational forces at play, stabilizing the wormhole and making it traversable. It's a concept that sounds like it belongs in a futuristic novel, but it's grounded in real scientific theory. The idea of traversable wormholes doesn't just challenge our understanding of singularities, it redefines them. Instead of being destructive endpoints, singularities could become gateways, linking distant corners of the universe in ways that were once thought impossible. Imagine stepping through a wormhole and emerging light years away, bypassing the limitations of space and time. It's a vision that could revolutionize interstellar travel, turning what was once the stuff of dreams into a tangible possibility. Of course, there's a lot we don't know. Exotic matter with negative energy has never been observed, and its existence remains purely hypothetical. Even if it does exist, the energy requirements to stabilize a wormhole would be staggering, far beyond anything humanity could currently achieve. And then there's the question of safety. What happens if the wormhole collapses while you're inside? These are just a few of the hurdles that make wormholes a tantalizing yet elusive prospect. But the concept of traversable singularities doesn't just raise questions about interstellar travel. It also challenges our understanding of the universe itself. If wormholes are possible, they could hint at a deeper structure to space-time, one that connects all things in ways we're only beginning to comprehend. They might even offer a way to reconcile the laws of quantum mechanics with general relativity, two frameworks that have long struggled to coexist. Wormholes remind us that the universe is full of surprises, and singularities are no exception. Whether they're cosmic dead ends or interstellar shortcuts, they continue to push the boundaries of what we think is possible. As we explore these ideas, we're not just dreaming of distant stars, we're reimagining the very fabric of reality. And who knows, what seems like science fiction today might just become science fact tomorrow. What if the birth of our universe wasn't a singular, explosive event, but the result of a cosmic collision? This is the heart of the Ecparotic universe theory, a bold idea that reimagines the origins of everything we know. Instead of a Big Bang, this theory suggests that our universe was born from the collision of two higher-dimensional brains, structures that exist in a realm beyond our familiar three dimensions. At the center of this collision, singularities, points of infinite density and gravity that might have acted as the engines driving this cosmic transformation. Picture this: two immense brains, each carrying its own singularity, moving through a higher dimensional space. When they collide, the energy released doesn't just create a single universe, it triggers a cycle of expansion and contraction, a process that could repeat endlessly. It's a vision of the cosmos as a dynamic, ever-changing entity, far removed from the static image of a one-time Big Bang. In this model, singularities aren't just remnants of a distant past, they're integral players in the ongoing drama of the universe. What makes the Ecparotic theory so compelling is how it reframes our understanding of cosmic cycles. Unlike the Big Bang model, which suggests a linear timeline with a definitive beginning and an uncertain end, the Ecparotic universe proposes a cyclical process where universes are born, expand, contract, and collide again in an endless loop. Singularities, in this context, become the catalysts for these cycles, driving the transformation of one universe into the next. It's a theory that challenges us to think of the universe not as a static stage, but as a living, breathing entity, constantly reinventing itself. But how does this collision of brains actually work? Imagine two sheets of paper floating in a three-dimensional space. When they collide, the energy from their impact ripples through both, creating the conditions for a new universe to form. The singularities within these brains act as focal points, concentrating the energy and shaping the new universe's structure. It's a process that's both elegant and chaotic, blending the precision of physics with the unpredictability of cosmic forces. The Ecparotic theory doesn't just challenge the Big Bang, it also offers a potential solution to some of cosmology's biggest puzzles. For example, it provides an explanation for the uniformity of the cosmic microwave background radiation, the faint glow left over from the early universe. In the Ecparotic model, the collision of brains naturally smooths out irregularities, creating the even distribution of energy we observe today. It's a theory that not only reimagines the universe's origins, but also deepens our understanding of its current state. Of course, this idea raises as many questions as it answers. What lies beyond the brains? Are there other universes out there, each born from its own collision? And if so, how do they interact with ours? These questions push the boundaries of our knowledge, inviting us to explore the cosmos in ways we've never considered before. The Ecparotic universe theory reminds us that singularities are more than just points of infinite density. They're the sparks that ignite the cosmos, driving its endless cycles of creation and renewal. Whether this model holds up to further scrutiny or not, it challenges us to think bigger, to see the universe not as a fixed entity, but as a dynamic, ever-evolving tapestry. And as we continue to unravel its mysteries, we're not just exploring the origins of our universe, we're uncovering the secrets of existence itself. What happens to information when it falls into a black hole? This question lies at the heart of one of the most perplexing mysteries in modern physics, the information paradox. At first glance, it might seem like a niche concern, but this paradox strikes at the very core of our understanding of the universe. On one hand, quantum mechanics insists that information, every detail about the state of a system, can never be destroyed. On the other, general relativity predicts that anything crossing a black hole's event horizon, including information, is lost forever, crushed into the singularity at its core. These two pillars of physics, each tested and proven in their own domains, appear to clash head-on when it comes to black holes. the stakes couldn't be higher. If information truly vanishes into a singularity, it would mean that one of the most fundamental laws of quantum mechanics, the conservation of information, is violated. This isn't just a theoretical hiccup, it's a crisis that could force us to rewrite the rules of the universe. But if information isn't destroyed, where does it go? Some physicists, including the late Stephen Hawking, proposed a groundbreaking idea. Maybe the information isn't lost at all. Instead, it could be encoded in the faint glow of particles escaping the black hole, a phenomenon known as Hawking radiation. Here's how it might work. As a black hole radiates energy, it slowly loses mass, eventually evaporating entirely. Hawking suggested that this radiation could carry away subtle imprints of the information that fell into the black hole, preserving it in a scrambled, almost unrecognizable form. It's like burning a book. The pages are gone, but the ashes might still contain traces of the words waiting to be decoded. This idea, known as the Hawking radiation solution, offers a glimmer of hope that the paradox might one day be resolved. But not everyone is convinced. Critics argue that even if information is encoded in Hawking radiation, the process of scrambling it could render it irretrievable, effectively making it as good as lost. Others propose even more radical solutions, such as the idea that black holes don't actually destroy information, but instead store it on their event horizons like a cosmic hard drive. This ties back to the holographic principle we discussed earlier, suggesting that the universe might have a built-in mechanism for preserving information, even in the most extreme environments. The debate over the information paradox isn't just a battle of theories, it's a quest to understand the very nature of reality. If information is truly conserved, even in the face of a singularity, it would imply a deeper order to the cosmos, a kind of cosmic bookkeeping that ensures nothing is ever truly lost. But if information can be destroyed, it would force us to rethink everything we know about the universe, from the smallest particles to the largest structures. What makes this paradox so fascinating is that it doesn't just challenge our scientific models, it challenges our intuition. It forces us to confront questions that go beyond physics, touching on the philosophical nature of existence itself. Is the universe fundamentally predictable, or are there regions where chaos reigns supreme? And if information can be preserved in the most extreme conditions, what does that say about the resilience of the cosmos? As we grapple with these questions, the information paradox remains one of the most tantalizing unsolved problems in physics. It's a reminder that even our most advanced theories are still works in progress, constantly evolving as we probe deeper into the mysteries of the universe. And while we may not have all the answers yet, the journey to uncover them is shaping the future of science, one singularity at a time. What if the event horizon of a black hole isn't the serene boundary we once thought, but a blazing inferno that obliterates anything daring to cross it? This is the startling idea behind the Firewall Hypothesis, a theory that turns our understanding of black holes on its head. According to traditional physics, an observer falling into a black hole would pass through the event horizon smoothly, unaware of their impending doom until reaching the singularity. But the Firewall Hypothesis suggests something far more dramatic, a scorching wall of energy at the event horizon, destroying anything that comes into contact with it. It's a concept so radical, it has sparked heated debates among physicists and forced us to re-examine the very nature of singularities. The Firewall Hypothesis didn't emerge from thin air. It was born out of a desperate attempt to resolve the information paradox we discussed earlier. If information can't be destroyed, as quantum mechanics insists, then what happens to the information of particles falling into a black hole? Some physicists argue that the only way to preserve this information is for it to be encoded in Hawking radiation, emitted as the black hole slowly evaporates. But here's the catch: for this to work, the radiation must be entangled with the particles inside the black hole. At the same time, the radiation must also be entangled with particles that escaped earlier. This creates a paradox, as quantum mechanics forbids a particle from being entangled with two separate systems simultaneously. Enter the firewall. To resolve this paradox, physicists propose that the entanglement breaks at the event horizon, releasing an immense burst of energy in the process. This energy forms a fiery barrier, incinerating anything that crosses it. It's a dramatic solution, but one that comes with its own set of problems. For starters, it contradicts Einstein's principle of equivalence, a cornerstone of general relativity, which states that an observer in free fall shouldn't notice anything unusual at the event horizon. If firewalls exist, they would shatter this principle, forcing us to rethink the very foundations of our understanding of gravity. The implications of this theory are profound. If firewalls are real, they would mean that black holes are far more violent and chaotic than we ever imagined. Instead of being smooth, predictable regions of space-time, they would be surrounded by a searing barrier of energy, transforming the event horizon into a cosmic kill zone. This raises troubling questions. Are black holes truly the serene, inescapable prisons we once thought? Or are they raging infernos that destroy anything that ventures too close? Of course, not everyone is convinced. Critics argue that the firewall hypothesis is more of a mathematical convenience than a physical reality, a patchwork solution to a deeper problem we don't yet fully understand. They suggest that the paradox it seeks to resolve might instead point to flaws in our current theories, hinting at a need for a new framework that unites quantum mechanics and general relativity. It's a reminder that, even in the face of radical ideas, science thrives on skepticism and debate. What makes the firewall hypothesis so fascinating isn't just its boldness, but the questions it forces us to ask. Are singularities truly the ultimate cosmic dead ends, or do they hide even more extreme phenomena waiting to be discovered? Could firewalls be the key to unlocking the mysteries of black holes, or are they a sign that our theories are still missing a crucial piece of the puzzle? As we continue to explore these ideas, we're not just probing the nature of singularities, we're pushing the boundaries of human knowledge itself. And in doing so, we're reminded that the universe is always ready to surprise us, challenging our assumptions and inspiring us to think bigger. What if the universe we see is just one thread in an infinite cosmic tapestry? This is the tantalizing possibility of the multiverse, a concept that suggests our reality might be just one of countless others, each with its own unique laws of physics, stars, and perhaps even life. But here's where things get even more intriguing. If the multiverse exists, could singularities be the bridges that connect these disparate worlds? Some theories propose that the singularities at the heart of black holes might not be dead ends at all. They could be cosmic doorways, linking our universe to others in ways we're only beginning to imagine. Take the idea of black holes and white holes, for instance. We've already explored how black holes pull everything in, while white holes, their theoretical opposites, push everything out. Now, imagine a scenario where a black hole in our universe connects to a white hole in another. Matter and energy that fall into the black hole here could be ejected through the white hole there, creating a kind of cosmic pipeline between realities. It's a theory that not only redefines the role of singularities, but also suggests that the multiverse might be far more interconnected than we ever thought. But how could such a connection even work? In this model, singularities wouldn't just be points of infinite density, they'd be the knots tying the multiverse together. Picture a vast network of universes, each linked by these cosmic tunnels, with singularities acting as the junctions. It's a vision that challenges the idea of isolation, suggesting that our universe might not be a lonely island in the void but part of a sprawling cosmic archipelago. Of course, this raises some mind-bending questions. If singularities are the gateways to other universes, what would those universes look like? Could they be vastly different from our own, with alternate laws of physics or entirely new forms of matter? And if so, what would that mean for the concept of reality itself? These questions push the boundaries of both science and imagination, inviting us to consider possibilities that stretch far beyond our current understanding. What makes this theory so compelling is how it reimagines the nature of singularities. Instead of being destructive forces, they become cosmic connectors, weaving the fabric of the multiverse into a single, interconnected whole. It's a perspective that not only deepens our understanding of singularities, but also challenges us to think bigger about the cosmos. Are we part of a multiverse? And if so, could singularities be the key to unlocking its secrets? As we explore these ideas, we're reminded that the universe, or multiverse, is full of surprises. Singularities, once thought to be the ultimate cosmic dead ends, might just be the most important crossroads in existence. Whether they're bridges to other realities or simply the product of our imagination, they continue to push the boundaries of what we think is possible. And in doing so, they inspire us to keep searching, keep questioning, and keep dreaming about the infinite possibilities that lie beyond the horizon. What if the most enigmatic force in the universe holds the key to understanding singularities? We're talking about dark energy, the invisible, repulsive force accelerating the expansion of the cosmos. While dark energy is often associated with the vast emptiness of space, some scientists are beginning to wonder if it might also play a crucial role in shaping the most extreme regions of the universe, singularities. Could this mysterious force, which seems to push galaxies apart at ever-increasing speeds, also influence the behavior of these cosmic anomalies? It's a question that opens up a new frontier in our understanding of singularities and their place in the cosmos. To see how dark energy might interact with singularities, let's first consider what we know about this elusive force. Dark energy makes up roughly 70% of the universe's total energy content, yet its nature remains one of the greatest mysteries in physics. Unlike gravity, which pulls matter together, dark energy acts as a kind of anti-gravity, driving the universe's expansion faster and faster over time. But what happens when this expansive force encounters the crushing gravitational pull of a singularity? The answer could reshape our understanding of both dark energy and the fate of singularities. One intriguing possibility is that dark energy might counteract the gravitational collapse that forms singularities in the first place. Imagine a star collapsing under its own gravity, destined to form a black hole. As the star's core shrinks to a point of infinite density, could dark energy's repulsive force intervene, preventing the singularity from fully forming? Some theories suggest that dark energy might create a kind of pressure that halts the collapse, leaving behind a dense but finite object instead of a true singularity. It's a scenario that challenges the very definition of what a singularity is, and whether such infinitely dense points can even exist in the presence of dark energy. But dark energy's influence might not stop there. If it can alter the formation of singularities, could it also affect their behavior once they're formed? For instance, dark energy might subtly change the way singularities interact with spacetime, potentially altering the properties of black holes or even the nature of the Big Bang Singularity. This idea raises fascinating questions about the relationship between the largest scale forces in the universe and the smallest, most extreme phenomena. Are singularities and dark energy locked in a cosmic tug-of-war, each shaping the other in ways we've yet to uncover? What makes this theory so compelling is how it connects the micro and the macro, the infinitely small and the infinitely large. Dark energy, a force that governs the entire universe, might have a direct impact on the most extreme conditions imaginable, blurring the line between the cosmic and the quantum. It's a reminder that the universe is a deeply interconnected system, where forces we once thought were separate might actually influence each other in profound and unexpected ways. Of course, this idea is still in its infancy, and many questions remain. How exactly would dark energy interact with a singularity? Could it truly prevent the formation of infinitely dense points, or would it merely modify their properties? And what would this mean for our understanding of black holes, the Big Bang, and the ultimate fate of the cosmos? These are the kinds of questions that keep physicists up at night, and they're exactly the kind of questions that push science forward. As we explore the role of dark energy in singularities, we're reminded that the universe is full of surprises. Forces we barely understand might hold the key to unlocking some of the greatest mysteries of existence. Whether dark energy prevents singularities from forming or simply reshapes their nature, it challenges us to think bigger, to see the cosmos not as a collection of isolated phenomena but as a dynamic, interconnected whole. And in doing so, it invites us to imagine a universe far stranger and more wondrous than we ever dreamed. What if the heart of a black hole isn't the chaotic, infinite abyss we've always imagined, but something far stranger? This is the essence of the Planck star hypothesis, a bold reimagining of what lies at the center of these cosmic giants. According to this theory, the core of a black hole might not be a singularity at all, but a densely packed, quantum-sized object known as a Planck star. Unlike the infinitely dense points predicted by classical physics, Planck stars are thought to be governed by the rules of quantum gravity, offering a radical new perspective on the nature of black holes and their mysterious interiors. To understand this idea, let's take a step back. In classical physics, a black hole singularity is a point where gravity becomes so intense that space-time itself collapses and all known laws of physics break down. It's a concept that's as unsettling as it is fascinating, leaving us with a paradox. How can something be infinitely dense? The Planck star hypothesis offers a potential answer by introducing quantum gravity into the equation. At the quantum level, gravity behaves differently, preventing matter from collapsing into a true singularity. Instead, it forms a Planck star, a tiny, ultra-dense object where quantum effects stabilize the core, preventing it from reaching infinite density. Imagine a black hole not as a bottomless pit, but as a cosmic onion. At its center lies the Planck star, a core so dense that it pushes the limits of our understanding, yet still finite. Surrounding it is the event horizon, the point of no return we're familiar with. This layered structure not only challenges our traditional view of black holes, but also offers a potential solution to the infamous black hole information paradox. If information isn't lost in a singularity but instead preserved within a Planck star, it could mean that black holes aren't the destructive forces we once thought. Instead, they might be cosmic vaults storing information in ways we're only beginning to comprehend. But how does this work in practice? Quantum gravity, the force that governs Planck stars, is still a theoretical framework, blending the principles of quantum mechanics and general relativity. In this model, the intense gravitational forces at the core of a black hole are counteracted by quantum pressure, creating a stable, finite object. It's like balancing a pencil on its tip, impossible under normal circumstances, but achievable with the right forces at play. This balance prevents the formation of a singularity, suggesting that the universe might have a built-in mechanism to avoid infinities altogether. What makes the Planck star hypothesis so compelling isn't just its challenge to classical physics, it's the questions it raises about the nature of reality. If black holes contain Planck stars, what happens to the matter and energy that fall into them? Could it eventually re-emerge, perhaps through quantum tunneling or other exotic processes? And if so, what would that mean for the ultimate fate of the universe? These ideas push the boundaries of our imagination, inviting us to rethink not just black holes, but the very fabric of existence. Of course, the Planck star hypothesis is still in its early stages, and many questions remain unanswered. How exactly does quantum gravity stabilize a Planck star? Could we ever detect one, or are they forever hidden behind the event horizon? And if Planck stars exist, what does that tell us about the underlying structure of the cosmos? These are the kinds of questions that drive scientific progress, reminding us that the universe is always ready to surprise us. As we explore the possibilities of Planck stars, we're not just probing the mysteries of black holes, we're uncovering clues about the nature of quantum gravity and the ultimate limits of matter and energy. Whether this theory holds up to further scrutiny or not, it challenges us to think bigger, to see the universe not as a collection of fixed rules but as a dynamic, ever-evolving puzzle. And as we piece together its secrets, we're reminded that the cosmos is far stranger and more wondrous than we ever imagined. What if time, the steady rhythm that guides our lives, doesn't just slow down near singularities, it stops altogether? When we think about singularities, especially those at the heart of black holes, we often focus on their immense gravitational pull or their ability to warp space. But what about time? Near a singularity, time doesn't just bend. It behaves in ways that defy everything we've come to expect. For an outside observer, time appears to slow to a crawl as an object approaches the event horizon, eventually freezing entirely. But what happens beyond that point? Inside a singularity, time might not just slow down, it might cease to exist as we know it. This is where the 14th theory comes in, exploring the bizarre and mind-bending ways time interacts with these cosmic anomalies. From the perspective of someone watching from a safe distance, time dilation near a black hole is a well-documented phenomenon. As an object falls toward the event horizon, its clock seems to tick slower and slower until it appears to stop entirely. This effect, predicted by Einstein's theory of general relativity, has been confirmed by observations of black holes and other massive objects. But here's the twist: while time grinds to a halt for the outside observer, the object falling into the black hole experiences something entirely different. From its perspective, time continues to flow normally, and it crosses the event horizon without even noticing. This disconnect between the observer and the falling object is one of the most perplexing aspects of black holes, raising questions about the very nature of time itself. But what happens once you're inside the singularity? This is where things get truly strange. Some theories suggest that time, as we understand it, might not even exist within a singularity. Instead of flowing forward in a linear progression, time could become meaningless, dissolving into a chaotic, timeless state. Imagine a place where past, present, and future blur together, where cause and effect no longer hold. It's a concept that challenges not just our understanding of singularities, but our fundamental perception of reality. Others propose an even more radical idea, that time inside a singularity could loop or even reverse. Picture a clock that doesn't just stop ticking but starts running backward, rewinding the flow of events. In this scenario, the singularity wouldn't just be a point of infinite density. It would be a cosmic reset button, turning the arrow of time on its head. This idea, while speculative, has profound implications. If time can loop or reverse within a singularity, it could mean that the laws of physics as we know them are not universal, but contingent on the specific conditions of spacetime. The role of time in singularities doesn't just challenge our scientific models, it forces us to confront deep philosophical questions. What does it mean for time to stop or reverse? How does our perception of time shape our understanding of reality? And if time behaves so differently near singularities, could there be regions of the universe where time operates in ways we can't even imagine? These questions push the boundaries of both science and imagination, inviting us to reconsider the nature of existence itself. As we explore these ideas, it's worth remembering that singularities are more than just theoretical curiosities. They're windows into the most extreme conditions the universe has to offer. By studying how time behaves near and within these cosmic anomalies, we're not just unraveling the secrets of black holes, we're uncovering clues about the fundamental nature of time. And in doing so, we're reminded that the universe is far stranger and more wondrous than we often assume. Whether time stops, loops, or disappears entirely within a singularity, one thing is certain: the journey to understand it is just as fascinating as the destination. What if the universe has a rulebook it refuses to let us break? This is the essence of the cosmic censorship conjecture, a bold idea that claims singularities must always be hidden behind event horizons, shielding the cosmos from their chaotic and unpredictable effects. Picture a singularity as a cosmic outlaw, so dangerous that the universe itself locks it away behind an impenetrable barrier, the event horizon. It's a concept that feels almost poetic, as if nature itself is enforcing order in the face of chaos. But here's the twist: what if this cosmic rule isn't always followed? What if some singularities break free, exposing their infinitely dense cores to the universe? This is the startling possibility that naked singularities present, and it could rewrite everything we thought we knew about the laws of physics. The cosmic censorship conjecture, first proposed by physicist Roger Penrose, is rooted in a simple yet profound idea: singularities are too extreme to exist in the open. Their infinite density and gravity would wreak havoc on spacetime, creating regions where predictability breaks down and the laws of physics as we know them cease to apply. By hiding singularities behind event horizons, the universe ensures that their destructive power remains contained, preserving the order and predictability we rely on to understand the cosmos. It's a comforting idea, almost as if the universe has built-in safety mechanisms to protect itself from its own extremes. But what if this cosmic censorship fails? The existence of naked singularities would shatter this comforting notion, exposing the universe to regions where the rules no longer apply. Imagine a singularity without its protective event horizon, a point of infinite density and gravity, free to influence the surrounding universe. In such a scenario, space-time would become a chaotic mess, and the very idea of causality, the principle that cause precedes effect, could break down. It's like trying to predict the weather in a storm that constantly rewrites its own rules. The implications are staggering, raising questions about the stability of the universe itself. The debate over naked singularities isn't just a theoretical exercise, it's a battle between order and chaos. On one side, the cosmic censorship conjecture offers a vision of a universe governed by predictable, well-defined laws. On the other, the possibility of naked singularities suggests a cosmos that's far more unruly and unpredictable than we ever imagined. Which side is right? The answer could depend on the conditions under which singularities form. For instance, some researchers argue that naked singularities might arise during the collapse of certain types of stars or in the chaotic aftermath of cosmic collisions. Others suggest they could be relics of the early universe, formed when space-time itself was still settling into its current structure. What makes this theory so fascinating isn't just its challenge to physics, it's the philosophical questions it raises. If naked singularities exist, they suggest that the universe is capable of producing regions where predictability fails, where the future becomes inherently unknowable. This idea forces us to confront the limits of human knowledge and the possibility that some aspects of the cosmos may forever remain beyond our grasp. Are we living in a universe governed by strict rules, or is it a place where chaos can erupt at any moment? The cosmic censorship conjecture offers one answer, but naked singularities suggest another, one that's far more unsettling and extraordinary. As we explore these ideas, we're reminded that the universe is full of surprises. Whether singularities are always hidden or occasionally exposed, they continue to push the boundaries of what we think is possible. And in doing so, they challenge us to think bigger, to see the cosmos not as a fixed entity but as a dynamic, ever-evolving puzzle. The cosmic censorship conjecture might be a comforting idea, but the possibility of naked singularities reminds us that the universe is always ready to defy our expectations. And that, in itself, is one of the greatest mysteries of all. What if the very concept of disorder holds the key to unlocking the secrets of singularities? Enter entropy, a measure of chaos and randomness that governs everything from the melting of ice to the collapse of stars. In the context of black holes and singularities, entropy takes on a whole new level of importance. The second law of thermodynamics tells us that in any closed system, entropy always increases, driving the universe toward greater disorder. But what happens when that system is a singularity, a point where the laws of physics as we know them break down? This is the heart of the 16th theory, the role of entropy in singularities, and how it challenges our understanding of the universe's most fundamental principles. Let's start with what we know. Black holes, those cosmic vacuum cleaners, are more than just gravitational powerhouses, they're also entropy factories. According to the work of physicist Jacob Bekenstein and later Stephen Hawking, black holes possess entropy, and a lot of it. In fact, the entropy of a black hole is directly proportional to the area of its event horizon, not its volume. This means that as a black hole grows, swallowing more matter and energy, its entropy skyrockets. It's a counterintuitive idea. A black hole, often seen as a region of pure destruction, is actually a reservoir of immense disorder. But here's where things get even stranger. What happens to that entropy when matter crosses the event horizon and reaches the singularity at the center? Does it continue to increase, or does it somehow vanish? One possibility is that singularities are regions of maximum entropy, places where disorder reaches its ultimate limit. In this scenario, the singularity isn't just a point of infinite density. It's also a point of infinite chaos, where the universe's tendency toward disorder is pushed to its absolute extreme. It's a concept that aligns with the second law of thermodynamics, suggesting that even in the most extreme environments, entropy still reigns supreme. But not everyone agrees. Some theories propose that singularities might actually violate the second law, creating regions where entropy decreases or even ceases to exist. Imagine a place where the universe's arrow of time, its relentless march toward disorder, is reversed or suspended altogether. It's a radical idea, one that challenges not just our understanding of black holes but the very foundation of thermodynamics. The debate over entropy in singularities isn't just a theoretical curiosity. It has profound implications for the nature of the universe. If singularities are regions of maximum entropy, they could represent the ultimate end state of matter and energy, a cosmic graveyard where disorder reaches its peak. But if they violate thermodynamic laws, they might hint at a deeper, more complex structure to the cosmos, one where the rules we take for granted no longer apply. This raises fascinating questions. Is entropy truly universal, or are there places in the universe where it breaks down? And if so, what does that mean for the fate of the cosmos? What makes this theory so compelling is how it bridges the gap between the macroscopic and the microscopic. Entropy, a concept that governs everything from the melting of ice to the expansion of the universe, might also hold the key to understanding the most extreme phenomena in existence. It's a reminder that the universe is deeply interconnected, with the same forces shaping the largest structures and the smallest particles. And as we explore these ideas, we're not just uncovering the secrets of singularities, we're redefining what we thought we knew about the nature of reality itself. The role of entropy in singularities is more than just a scientific puzzle, it's a window into the universe's deepest mysteries. Whether singularities obey the laws of thermodynamics or defy them, they challenge us to think bigger, to see the cosmos not as a fixed entity but as a dynamic, ever-evolving system. And in doing so, they remind us that the universe is always ready to surprise us, pushing the boundaries of what we think is possible. As we continue to unravel these mysteries, one thing is certain: the journey is just as fascinating as the destination. What if singularities aren't just cosmic dead ends, but the engines driving the evolution of the universe itself? This is the heart of the 17th theory, a bold reimagining of singularities as not just destructive forces but creative ones. Instead of being the final stop in the cosmic journey, singularities might act as catalysts, shaping the universe in ways we're only beginning to understand. From triggering the birth of new universes to driving the expansion of our own, these enigmatic phenomena could hold the key to some of the most profound mysteries of existence. Let's start with the idea of singularities as cosmic nurseries. Imagine a black hole, its immense gravitational pull crushing matter into an infinitely dense core. Now, what if that core isn't just a point of no return, but a seed for something entirely new? Some theories suggest that under the right conditions, a singularity could give rise to an entirely new universe separate from our own. This process, known as universe birthing, proposes that the extreme conditions within a singularity could trigger a new Big Bang, creating a bubble of space-time that expands into its own cosmos. It's a concept that transforms singularities from endpoints into beginnings, suggesting that the universe might be part of an endless cycle of creation and destruction. But the creative potential of singularities doesn't stop there. What if they're also driving the expansion of our own universe? We've already seen how dark energy is pushing galaxies apart at an accelerating rate. But could singularities play a role in this process? Some physicists speculate that the energy released by singularities, whether through quantum effects or exotic processes we've yet to discover, might contribute to the universe's expansion. In this scenario, singularities aren't just passive observers of cosmic evolution, they're active participants, shaping the very fabric of space-time. This theory doesn't just challenge our understanding of singularities, it redefines their role in the cosmos. Instead of being isolated, destructive anomalies, they become integral to the universe's ongoing story. Whether through birthing new universes or driving the expansion of our own, singularities might be the unseen architects of cosmic evolution. It's a perspective that shifts our focus from the chaos they create to the order they might sustain, offering a new way to think about the universe's most extreme phenomena. Of course, this idea raises as many questions as it answers. How exactly would a singularity trigger the birth of a new universe? What role does quantum gravity play in this process? And if singularities are contributing to the expansion of our universe, how do we detect their influence? These are the kinds of questions that push the boundaries of science, inviting us to explore the cosmos in ways we've never considered before. What makes this theory so compelling isn't just its challenge to traditional views, it's the way it connects the microscopic to the cosmic. Singularities, once thought to be isolated points of infinite density, might actually be part of a larger, interconnected system, driving the evolution of the universe on the grandest scales. It's a reminder that the cosmos is a dynamic, ever-changing entity, shaped by forces we're only beginning to understand. As we explore these ideas, we're not just uncovering the secrets of singularities, we're piecing together the story of the universe itself. Whether they're birthing new realities or shaping the one we inhabit, singularities challenge us to think bigger, to see the cosmos not as a static backdrop but as a living, evolving tapestry. And in doing so, they remind us that the universe is always ready to surprise us, offering new mysteries to unravel and new stories to tell. What if the very act of observing the universe could change its most extreme phenomena? This is the tantalizing possibility at the heart of the 18th theory, the role of consciousness in singularities. While singularities are often thought of as purely physical phenomena, governed by the laws of gravity and quantum mechanics, some speculative theories suggest that consciousness, our ability to observe and interpret the universe, might play a crucial role in shaping their behavior. It's an idea that blurs the line between science and philosophy, challenging not just our understanding of singularities, but the very nature of reality itself. To grasp this concept, let's start with a principle from quantum mechanics, the observer effect. In the quantum world, particles don't have definite properties until they're observed. The act of measurement itself can influence the state of a particle, a phenomenon famously demonstrated by the double-slit experiment. Now, imagine applying this idea to singularities, regions where the laws of physics as we know them break down. Could the act of observing a singularity, even indirectly, influence its properties? Some theorists propose that consciousness might interact with singularities in ways we don't yet understand, potentially altering their behavior or even their very existence. This idea isn't just speculative, it's rooted in some of the most cutting-edge thinking at the intersection of physics and philosophy. For instance, the participatory universe hypothesis suggests that the universe requires an observer to bring it into existence. In this view, consciousness isn't just a passive bystander, it's an active participant in shaping reality. If true, this could mean that singularities, like all other phenomena, might be influenced by the presence of conscious observers. It's a concept that transforms singularities from isolated cosmic anomalies into phenomena deeply connected to the fabric of existence itself. But how could this work in practice? One possibility is that consciousness might act as a kind of feedback loop, influencing the quantum fluctuations that occur near singularities. These fluctuations, which are inherently probabilistic, could be shaped or stabilized by the act of observation, potentially altering the singularity's behavior. Another idea is that consciousness might interact with the information encoded on a black hole's event horizon, as suggested by the holographic principle we explored earlier. In this scenario, the observer doesn't just measure the singularity, they become part of its structure, weaving their own consciousness into the cosmic tapestry. Of course, this theory raises as many questions as it answers. What does it mean for consciousness to influence a singularity? Could it alter the flow of time, the behavior of gravity, or even the fate of matter and energy within a black hole? And if consciousness does play a role, how do we measure or test its effects? These questions push the boundaries of both science and philosophy, inviting us to explore the universe in ways we've never considered before. What makes this theory so compelling isn't just its challenge to traditional physics, it's the way it bridges the gap between the objective and the subjective. Singularities, once thought to be purely physical phenomena, might actually be shaped by the very act of observing them. This idea forces us to confront deep questions about the nature of reality. Is the universe a fixed, objective entity, or is it shaped by the consciousness that perceives it? And if consciousness does play a role, what does that mean for our understanding of existence itself? As we explore these ideas, we're reminded that the universe is far more mysterious and interconnected than we often assume. Whether consciousness influences singularities or not, the very possibility challenges us to think bigger, to see the cosmos not as a collection of isolated phenomena, but as a dynamic, ever-evolving system. And in doing so, it invites us to imagine a universe where the boundaries between observer and observed, between science and philosophy, are far more fluid than we ever thought possible. What if singularities aren't just cosmic anomalies, but the ultimate time machines? This is the intriguing possibility at the heart of the 19th theory, the role of singularities in time travel. We've already seen how these infinitely dense points can warp spacetime to extreme degrees, creating regions where the normal rules of physics no longer apply. But what if that warping could be harnessed? Could singularities, with their immense gravitational pull, become the key to unlocking the secrets of time travel? It's a concept that sounds like science fiction, but some of the most respected theories in physics suggest it might not be as far-fetched as it seems. Let's start with the idea of traversable wormholes, cosmic shortcuts through spacetime that could connect distant regions of the universe. As we've explored earlier, wormholes are thought to contain singularities at their cores, points where spacetime is bent so drastically that it creates a bridge between two locations. But here's where it gets even more fascinating. If a wormhole could be stabilized, perhaps with exotic matter or advanced technology, it might not just connect distant places, it could link different moments in time. Imagine stepping into one end of a wormhole and emerging years, centuries, or even millennia in the past or future. It's a vision that transforms singularities from cosmic dead ends into gateways through time. But how could this work in practice? One possibility lies in the concept of closed time-like curves, theoretical loops in spacetime that allow for backward time travel. In this scenario, a singularity's immense gravity could twist spacetime so severely that it creates a path where time folds back on itself. Picture a clock that doesn't just tick forward but loops, allowing you to revisit moments you've already experienced. It's a mind-bending idea, one that challenges our most fundamental understanding of causality, the principle that cause must always precede effect. If closed time-like curves exist, they could open the door to paradoxes like the infamous grandfather paradox, where traveling back in time could create contradictions that defy logic. Of course, the idea of time travel through singularities raises as many questions as it answers. For starters, how could we stabilize a wormhole or create a closed time-like curve without violating the laws of physics? The energy requirements would be astronomical, far beyond anything humanity could currently achieve. And then there's the question of safety. What happens if the wormhole collapses while you're inside, or if the closed time-like curve becomes unstable? These are just a few of the hurdles that make time travel through singularities a tantalizing yet elusive prospect. What makes this theory so compelling isn't just its challenge to our understanding of time. It's the way it reimagines singularities as tools rather than obstacles. Instead of being cosmic dead ends, they become potential gateways to new possibilities, offering a way to explore the past, the future, and everything in between. Whether or not time travel through singularities is possible, the very idea pushes the boundaries of what we think is achievable, inviting us to dream of a universe where the flow of time is no longer a one-way street. As we explore these ideas, we're reminded that the universe is full of surprises. Singularities, once thought to be the ultimate cosmic dead ends, might actually be the key to unlocking some of the greatest mysteries of existence. Whether they are gateways to other universes, engines of cosmic evolution, or even time machines, they continue to push the boundaries of what we think is possible. And in doing so, they inspire us to keep searching, keep questioning, and keep dreaming about the infinite possibilities that lie beyond the horizon. What becomes of singularities when the universe itself grows old? As we peer into the distant future, billions or even trillions of years from now, the fate of these cosmic anomalies becomes a question of profound importance. Singularities, those infinitely dense points at the heart of black holes and the birth of universes, might not be eternal after all. Over unimaginable timescales, they could transform, evaporate, or even give rise to entirely new realities. This is the 20th theory, the ultimate fate of singularities and how they might shape the universe's final chapter. Let's start with the most well-known scenario, Hawking radiation. Stephen Hawking famously proposed that black holes aren't entirely black. Instead, they emit a faint glow of particles, slowly losing mass and energy over time. This process, known as Hawking radiation, suggests that even the mightiest black holes will eventually evaporate. For stellar mass black holes, this could take billions upon billions of years. But for supermassive black holes, the timeline stretches into the far, far future. As they shrink, their singularities, once thought to be eternal, could vanish entirely, leaving behind nothing but a whisper of radiation. It's a poetic end, one that transforms singularities from cosmic immortals into transient phenomena. But what if Hawking radiation isn't the only path? Some theories propose that singularities might not simply fade away, they could collapse into new universes. Imagine a black hole, its singularity compressed to an unimaginable density, reaching a point where the fabric of space-time itself tears open. In this scenario, the singularity could trigger a new Big Bang, birthing a universe entirely separate from our own. It's a concept that turns the end of one cosmic story into the beginning of another, suggesting that the universe might be part of an endless cycle of creation and destruction. In this view, singularities aren't just endpoints, they're seeds capable of sprouting entirely new realities. Then there's the possibility that singularities persist indefinitely, enduring even as the universe around them changes. In a cold, dark cosmos trillions of years from now, where stars have burned out and galaxies have drifted apart, singularities might remain as the last vestiges of structure. These lonely remnants hidden in the void could become the final landmarks of a fading universe. But even here, the story isn't simple. Quantum mechanics suggests that nothing lasts forever, not even singularities. Over unfathomable timescales, they too might succumb to the relentless march of entropy, dissolving into the cosmic background. What makes this theory so compelling is how it ties the fate of singularities to the fate of the universe itself. Whether they evaporate, collapse, or persist, singularities are more than just cosmic oddities, they're key players in the grand narrative of existence. Their ultimate fate could tell us whether the universe is destined to fade into darkness, cycle endlessly through rebirth, or settle into a state of eternal stillness. Each possibility offers a different vision of the cosmos, challenging us to think beyond our own fleeting moment in time. As we explore these ideas, we're reminded that the universe is a dynamic, ever-changing entity. Singularities, once thought to be static and unchanging, might actually be part of a much larger story, one that unfolds over timescales we can barely comprehend. Whether they vanish, transform, or endure, they continue to push the boundaries of what we think is possible, inviting us to imagine a universe far stranger and more wondrous than we ever dreamed. And in the end, that's what makes them so fascinating, not just as scientific puzzles, but as windows into the ultimate nature of existence itself. From the crushing depths of black holes to the explosive birth of the universe in the Big Bang, cosmic singularities have taken us on a journey through the most extreme and enigmatic corners of existence. These 20 theories aren't just scientific curiosities, they're invitations to rethink everything we thought we knew about space, time, and reality itself. Each idea, from the Planck star hypothesis to the Firewall paradox, challenges us to confront the limits of our knowledge and imagine possibilities that stretch far beyond the ordinary. Singularities aren't just cosmic anomalies, they're windows into the deepest mysteries of the cosmos, forcing us to question what we consider possible or even real. What's truly remarkable about these theories is how they bridge the gap between the known and the unknown. They remind us that the universe isn't just a collection of stars and galaxies, but a dynamic, ever-evolving system governed by forces we're only beginning to understand. Whether singularities are gateways to other dimensions, engines driving the birth of new universes, or simply puzzles waiting to be solved, they show us that the cosmos is far stranger and more wondrous than we often assume. These ideas don't just expand our understanding, they ignite our imagination, inviting us to dream of realities beyond our current grasp. But here's the thing, the journey doesn't end here. The more we learn about singularities, the more questions they raise. What lies beyond the event horizon of a black hole? Could the Big Bang Singularity have been part of an endless cosmic cycle? And what role do these extreme phenomena play in the grand tapestry of the universe? These are the kinds of questions that keep scientists and curious minds like yours awake at night, pushing the boundaries of what we know and inspiring us to explore further. So, what do you think lies beyond the singularity? Do you believe they're cosmic dead ends, gateways to other realities, or something even more extraordinary? Share your thoughts in the comments below. We'd love to hear your ideas and spark a conversation about the universe's greatest mysteries. And if you've enjoyed this deep dive into the strange and wonderful world of cosmic singularities, don't forget to subscribe and hit the notification bell. There's so much more to explore, from the secrets of dark matter to the mysteries of quantum gravity, and we're just getting started. Thanks for joining us on this journey. See you in the next